Hello, once again, all of my friends. This is the SMC Journal podcast, the show that's all about software engineering in today's modern IT. I'm Scott Moore, your host. Thanks for joining. I'm very excited about today's show, and so is Agent 503, who has adopted the either Joe Satriani, James Pulley, or Paul Grisafi look for some reason. I'm excited about today's show and a little hyped up because my guest today, when we're talking about performance engineering, we are talking about an engineer in the true sense of the word, but somebody who has given back to the community by writing a fabulous book that has been out there for a while, but it never grows old because it was a far-sighted book in the sense that it's providing information that all performance engineers can use all the time. We're going to talk about that on today's show. Before we do, let's talk about the sponsors that make this show possible for you to watch. This podcast is sponsored by Bryte Payment Solutions. They provide merchant services for a wide variety of credit card companies. They take most major credit cards at the lowest rates and fees possible, and they can help your business generate higher revenue through a variety of payment solutions they have, including their own point-of-sale equipment and custom software. If you take credit cards for your business, you should contact them and see how they can help you. Go to brighteps.com and tell them Scott Moore from the SMC Journal sent you. So my guest today is Andre Bondi, and he is the author of a book called Foundations of Software and System Performance Engineering. And we're going to talk about that today, but I also want you to just be introduced to Andre. He's also taught classes, written a lot of white papers on the topic of performance engineering, and just such a knowledgeable person. So without any more hesitation, here's Andre. Andre, welcome to the SMC Journal podcast. Great to have you.
Finally, we get to meet.
I know, exactly. I mean, it's been probably more than a decade that we've known of each other, and we cross post and all that stuff. And I've read your material, and you're awesome. I learned a lot of stuff from you. I'd like for you to introduce yourself to our audience of people who might not know who you are and how you got involved in performance engineering.
I'm Andre Bondi. I got involved in performance engineering quite by accident in the early days of the Golden Age. I was doing a degree in statistics at University College London, and I didn't quite know what to do with myself. And the careers advisor suggested that I contact a company called Logica because they were hiring all sorts of people. And also, they happened to be the UK reps for Best One, Jeff Boozen's queuing analysis tool. And I had done some queuing theory in grad school as part of my statistics degree. And suddenly this all made sense. And I decided that that was what I wanted to do. And then I decided that I really wanted to do graduate work in the area. And I wound up at Purdue University, where Peter Denning was at the time, who had worked with Jeff Boozen on operational analysis. And from there, I went to teach at Santa Barbara, UC Santa Barbara, for 3 years. I taught simulation, performance modeling, and operating systems. And the cross-fertilization between operating systems and performance evaluation is really important because the way my professor taught it, you tend to think of the operating system as containing a network of queues, which is susceptible to modeling. But of course, you have to think about what's happening underneath the queues and all kinds of strange interactions that are going on. Then I was at Bell Labs for 12 and a half years, something like that. This was a time when Bell Labs and AT&T Labs together had more queuing theorists under one roof than any other facility in the world, more people doing performance than any other facility in the world. So I was trying to not just be a mathematical modeler, but also try and understand what the system interactions were and start thinking about the system thinking about the performance of the system in systematic terms. And there was another aspect of my work at Bell Labs and my colleagues' work at Bell Labs, a long tradition actually of traffic management and modeling. And this is something that carries over into the web as well. You need to understand how the traffic is going to vary at different times of the day, and with the seasons, so that you can deploy the resources appropriately in anticipation of when you're going to need them, but also do it robustly so that you can handle the surge of traffic. In those days, a surge of traffic consisted of people calling an 800 number during a commercial during the Super Bowl. Nowadays, there would be a web search, or people would pull out their phones, or something like that. But it's the same link between traffic and human behavior.
Correct. Yes. Um, this is fascinating because you've been involved in some things that very few people in our industry get to see. And then you look at today's IT world. Do you see that that are graduates with CS degrees that they're getting this type of basic information around performance engineering? Because I don't see it, and it's a concern of mine.
You're absolutely right. It's not there. And this gives me a useful segue, actually. Nowadays, the interactions between system components are so complex that it's difficult to have a model, to build a model that really captures the scope of how things behave. It's necessary to focus on models of where the bottlenecks are likely to appear. I teach performance testing, which I learned by rubbing shoulders with my colleagues at Siemens who were doing performance testing. I was in the software engineering department at Siemens Corporate Research, as it was called at the time, then Corporate Technology. And I tried to get my students used to the idea that you not only want to think about how the components of the system are interacting with each other, how you're going to be doing integration testing, and so on. You want to think about structuring the system to be functionally testable, but also structuring the system to be testable from a performance standpoint as well.
Mhm.
So, do you start testing when do you start doing performance testing when you're doing unit testing? Do you do global performance testing when you're doing integration testing? That kind of thing. All those things are very important because they allow you to uncover bottlenecks before you take the pieces of a system and put them together. And they force you to think about what the performance requirements are going to be at each layer and how each outer layer is going to be driving the load at an inner layer. And the performance is not only about the transactions that are driving the system, you also have to think about the housekeeping that's going on and the performance requirements for that. And actually, I'm surprised that this is not thought about more in the industry because there was even work in the early 1980s that described how you run processes in the background to clean up stale database records so as to cut down the search time, because traditionally you don't physically delete a record. You just mark it as deleted, but that means you still have to skim past it when you're doing a traversal.
Right.
And purging that makes the searches shorter. And this is something that a database person linked with a performance person would think about.
But not necessarily the developer when writing that feature or function, which is a problem. And
Exactly.
when we move into the world of DevOps, where we have the pure DevOps players saying, listen, the developers have to do it all. I want help from you specialist performance engineers, but stay out of my way. You need to make it easier for me to do it in my IDE as I'm doing this code, and I will do it if you make it easy for me. But if you try to do it for me, you have now become the bottleneck in the pipeline and prevented me from rolling this software out to production. What do you say to that?
I say that it's necessary to equip the IDE with performance hooks that show where the program is spending its time at every step of the performance lifecycle, whether you're doing, and by the way, that's the case whether you're doing it in Agile or whether you're doing a waterfall model or something in between. Um, there are two problems here. One is to motivate the developer to actually think about this, not only in terms of how the different layers of the system feed into each other, but in terms of the algorithm, giving a lot of thought to the algorithms that are going to be used to implement, and giving a lot of thought also to the space-time trade-off, and if they're working in a Java environment, whether there's going to be garbage collection that's going to mess things up, and how you minimize the amount of garbage that has to be collected. Subtleties like that. And also, they should understand that they can use performance measurements to identify bugs that could really be destructive to system functions, such as memory leaks. If you leak too far, you can bring a system down.
Correct.
And you need to design to make sure that you don't have the leaks. And then you need to instrument when you're doing the testing and be prepared to do the testing long enough to identify those memory leaks.
There is
If
so much to be gained by making these optimizations early that you get out of this instead of having to find it out later through a dev oops moment. You know what I mean?
Exactly.
Um, So that's why I try to emphasize the need for the specialization. And there's also a scope to this, right? A developer is thinking about performance around the code they're writing for that function, but they're not necessarily thinking about the things that aren't part of their code, their world of code. There's things that we have to test and optimize that have nothing to do with the software code. I mean, the infrastructure itself, the network itself, all of these play a
Absolutely.
role as well. So we have a much bigger view of performance of that. And I think that gets forgotten sometimes.
You can't think of performance, you can't think of networks as being an unlimited resource. There's always going to be a saturation point or a bottleneck somewhere. So you need to think about how it's going to be loaded. There's no, I don't want to say there's no free lunch because that's a cliche, but there's no free usage. There is nothing that is without limits.
Correct. Including the cloud.
There is nothing that is without resource limits. It's just that you might not have reached it yet. And
That's
by
right.
the way, if you're paying for the resource, which is what you're doing in the cloud isn't unlimited either, which is why I admire the work that the people at Capacitas and other places are doing, trying to optimize cloud spend and understanding where the system is spending its time.
So, what do you think about the FinOps revolution that we're seeing out here, which is basically stop spending so much money in the cloud and here's how you do it? To me, it would seem like performance engineers and FinOps should be working hand in hand because it's about efficiency. We want things fast, but we also want things to be efficient, and that means less cost, right?
Yes, absolutely. Absolutely. And that means understanding how to navigate the space time trade off, understanding what efficiencies you can introduce in your design. But there's something else going on. There are a couple of other things that I wanted to mention as well. One is that when you're doing DevOps, that means that you're going to be doing constant build or recompilation or whatever it happens to be. You want to think about how you can engineer that process so as to take the minimum amount of time because that's going to reduce your time to production.
Right.
And it's also going to, if you want to iterate quickly, you need to be able to compile or build quickly. So thinking about the performance considerations of doing that is very important. The other thing is that there's a misconception that people like me are only mathematicians who want to build models. It really behooves us, and this was something that I had to learn the hard way in my not terribly misspent youth. You need to think about how the system resource usage informs your modeling and vice versa. You need to think about what the tools are that are going to be tweaked. On the other hand, right now, I see that there's a tremendous emphasis on performance testing. Certainly, when I look at recruitment ads, they want people to write scripts to do performance testing. I'm not convinced that the people who are doing that understand how to structure a test so that it's a performance test, so that it's going to be as informative as possible.
Correct.
Not only from the standpoint of the use cases, but so you can understand the nuts and bolts of what's happening behind the scenes. I'm not convinced that they're doing that. And somehow we need to get the point across that there's a true value add here. It's a bit like buying insurance in a way, because you're trying to anticipate problems and you have a success when you don't have a problem.
Right. I can't tell you the times that I have come behind a big five, big four consulting organization that has separated the building of the scripts and the running of the test from analysis and the planning. And we have trusted that the people just writing scripts blindly sometimes that they're setting it up and creating scenarios that are realistic at all. And so the output of the analysis becomes invalid, in my opinion. And that is probably the biggest downfall that I've seen. But I have made a lot of money cleaning up after these messes. So I don't know how much I'm motivated to fix that problem. You know what I mean?
Right. Well, actually, one of the I spent some time training performance testers in my mindset when I was at Ferguson for a year and a half. Uh, my manager, Saurabh Jain, was very far-sighted. He turned me loose. And one of the things that I explained to people was that you can't look at the average statistics from end to end. You have to look at the ramp-up time. You have to look at whether the system is reaching a steady state in the first place. If it's not, the statistics are meaningless.
Correct.
The
Yes.
averages are completely misleading. You need to look at the spikes. You need to look at how the system is behaving during ramp up. You need to look for Basically, if the underlying assumptions of a performance model are not satisfied, there is probably something very wrong with the system. So, for instance, if you're doing, but let's suppose that you're doing a massive database read overnight or a massive database cleanup overnight. There are no transactions going on externally because it's nighttime or you've cut the users off or whatever. But if you see the CPU utilization going up with the square of the time, that should tell you something about the algorithm that's being used to do whatever the processing is.
Right. Right.
And that's a problem waiting to happen because you may not get the batch job finished on time.
Which is a domino effect later.
Exactly. And on the other hand, if you're doing a transaction-based system and you're testing at a constant rate, which is what you should be doing, and you're not seeing constant utilizations with sufficiently large granularity, by the way, so every 30 seconds or every minute rather than every second, so as to smooth out the noise. If you're not seeing smooth behavior, constant behavior, if you're seeing increasing memory consumption or something like that, there is something going on in the system that needs to be fixed. And doing that as soon as you spot the problem can save you a lot of grief later. It's rather like the Japanese car factory that was all the rage in the 1980s. They would talk about the worker on the assembly line seeing too many defects and being able to pull a red rope in order to bring the line to a stop so that the problems wouldn't be built into the car down the line. That is the kind of mindset that needs to be encouraged, I think. And people are reluctant to do that because they're measured on their deliverables rather than necessarily the quality of the deliverable. I can't tell you how many times developers have said to me, well, we have to get the product out.
Yes, because nothing
Never
sounds
mind
like
the
money.
crash as soon as it goes out.
Nothing sounds like money like production code, is what I've been told. So,
But if it's lousy production code, then it incurs ill will.
yes. And so that's why I've always maintained that the performance engineers really should be the rock stars of the company, whatever company, because we want the same things that the C-level wants. In the end of the day, we want lower risk, we want most efficient, cost effective, fast software that everybody loves. It's always a win-win when we get to do our job. And I'm always concerned how I'm seeing in the industry how our discipline has sort of been pushed to, well, you're non-functional requirement people. And I don't know how that happened, but I'm not sure that.
If you don't fix the non-functional requirements, the system will be non-functional.
Correct. And if you say it's functional, but it's only functional for one and not for many, it's not functional in my opinion. And so I think maybe the problem was that over a certain period of time, people in our industry that were doing just the testing, they weren't doing good analysis, they weren't providing the value, they weren't telling the story that they should have been telling to show how much value we were providing. And that's what I think needs to change.
I agree with you. And it's particularly important in mission critical systems as well. I had a wonderful time during the 12 years or so that I was at Siemens because I had a different set of control systems to work on every year or two. I worked on building management and surveillance systems, which are not that different from a classical network management system in a way, because you're monitoring data, you're monitoring traffic and seeing what's happening. And also you're triggering interventions when something is going awry. And then you need to think about what the performance requirements are for a particular use case. And some of them aren't necessarily steady state. For instance, when you're dealing with a fire alarm system, you have to get people out of the building, and there's a requirement. In Europe, it's 5 seconds from detection of smoke to a noise being emitted. So you get people out of the building. But that isn't all that a fire alarm system does. It closes windows, it notifies the fire department, it closes doors, it opens vents or closes vents or something like that. And understanding that you need to be able to cope with a burst and understanding how big that burst of messages is going to be so that you can trigger the alarm is just as legitimate a performance question as you would find in any transaction-oriented system. But it's a different kind of mindset. Yes, you're doing the monitoring and you want to see You want to make sure that the system is functioning normally and so on, that there's no smoke. But when you're in panic mode, you want to make sure that you get the word out very quickly so you get the building evacuated and make sure that the flammables are isolated and things of that nature. And similarly, when you're controlling aircraft, you need to make sure that the messages are relayed to the engines that you're going to up the throttle or lower the throttle or lower the flaps or whatever it happens to be. And similarly, with trains, you have to get the message out to the train that it's got to stop a long way beforehand, because the stopping distance of a train running at 200 kilometers an hour might be 7 kilometers.
Correct. Yeah. I mean, it's
And
it's the mindset.
at 200 kilometers an hour, you're going to traverse that distance in a matter of seconds.
Yes, it's amazing the mindset change that has to be in place to think about this ahead of time. And that kind of brings me to the next segment here, where you have spent a lot of your time giving back as you've learned, and you educate people all the time. I would be taking your class right now if I could. I feel like there's so much that I need to go back over again just to keep up. But you've provided a lot of information in a book that you've written. So let's talk about your book for a second, okay?
So
This is something that I've recommended before, and I will recommend again. I'm recommending today. I want to show it. It's a book that you wrote back in 2014 called Foundations of Software and System Performance Engineering, Process, Performance Modeling, Requirements, Testing, Scalability, and Practice. Now, that's a mouthful, and that sounds like you've got it all here. So tell me and our audience about this book.
the idea here is that there's a relationship between what happens in the performance engineering lifecycle and what happens in the software development lifecycle. You're thinking about the application and you're thinking about the requirements. That's going to inform the design and the architecture. And eventually, you're going to go down and start thinking about how you're going to structure the tests to make the performance tests and what kind of measurements you have to collect in order to make sure that you understand how the system is working. Not only so that you can verify that you're meeting performance requirements, but so that you can anticipate problems that are going to arise. And so you can understand where you might want to extend your test plan to implement stress testing to see if you can provoke the kinds of problems that you suspect are happening from the first round of measurements that you're taking. And the reason that this flowchart has loops is it's an iterative process. It's an iterative process whether you're in the waterfall framework or an agile framework, because you're learning from what you're seeing, not only to fix any performance issues that arise in the course of your initial activities, but also because when you're adding features, you're going to be working on the same platform. You need to make sure that those features are not going to degrade the performance of what you have already. And you need to make sure that the features that you're adding are also going to meet the requirements of the new features while not hurting the performance of the old ones. And it's not just the steady state performance, response time, and throughput, and so on. You want to make sure you're not provoking any problems with new features that might bring the system down.
You know, the thing that I love about this book is that it's tool neutral. It's the deployment method neutral. This is not a book that you're going to read once like a novel and go, oh, that was a good story. This is a reference material book. And as you go through it, every project, you might go back and say, let me go back through that section again around, say, performance requirements, or how you actually put together a realistic performance scenario and some of the formulas that you might use to calculate some of the things around queuing theory, for example. So I love the fact that you put that in there. And I want to just mention the importance that you place on performance requirements and gathering around this. And is that just because that is something that you focused on early on, or maybe you got bit on that from not doing it properly? Because I find that a lot of people who start doing load testing and performance testing, they want to get right to the scripting and the testing because it's the technical stuff. They're sitting in front of a computer doing some geeky things, but they don't spend a lot of time on the how are we going to put this test together so that it matches what the business is actually doing. They kind of skip that. And even in the classes that they take, when the tool vendors are talking about the importance of planning, they kind of skip that. Is that why you put so much emphasis in the book around that?
There are a couple of reasons why I did that. One was that there have been cases in which the expectations were not explicitly stated, and the end user was unhappy, or the system owner was unhappy. because the system didn't do what he or she was hoping it would do. But that may have been also because of a lack of specification and a lack of expectation management. And another reason I got into it was that we wanted to contractually oblige vendors to provide the kind of performance, the kind of system throughput, the kind of response times, the kind of robustness that the system was going to need right out the door. As a criterion for acceptance, we want to attach penalties, if you like, for not meeting performance requirements, but you can't enforce that unless you specify the performance requirements very explicitly. So this is where there's a link between performance and the business side and the engineering need, and also the legal side, by the way. You want to make sure that those requirements are written in measurable terms. That in turn is going to drive how you instrument the system. But on the other hand, you might decide that you don't want to take those measurements because it's too expensive. There may be a trade-off there. So you need to talk to the business people and ask if you can afford, figure out if you can afford not to take those measurements, and also work with the legal department to make sure that you're not expressing a requirement in terms that cannot be enforced. If you can't measure it, you can't enforce the requirement.
I would bet you that it's less than one hand how many times the performance requirements have been consulted by the legal department in percentage wise. That's probably the first time I've heard that, but that's a great idea.
Not since my AT&T days.
Yes, but so that those are important, especially the more mission critical that you get. I want to give people a little bit of an insight of what they can get out of this book if they get it. In chapter 11, you talk about scalability and performance, and you talk about the different types of scalability. So you mentioned load scalability, space-time scalability, structural scalability. Can you just briefly kind of walk through how you came up with those, what those mean?
Yes, I can. With load scalability, I wanted to underscore that the system has to perform very well as the load increases. If you think of this being this being the load axis and this being some kind of performance metric axis, a response time axis, if you like, you want the response time to be increasing very slowly as the load increases. You want the system to function gracefully, and even function gracefully if there's a spike. That is how I came up with the notion of load scalability. With space scalability, we wanted to make sure that as you increase the number of objects that a system has under management, say in a network management system or in a database that's supporting a business system with an increasing number of clients or an increasingly broad range of inventory or something like that, that the system can cope with it. Structural scalability is something that I came up with when I was looking at the way network protocols behave. In the early days of broadband, the throughput that you could obtain was limited by the window size. That in turn is limited by a field in the TCP packet header that tells you how many packets how much data you can have outstanding. The window size is byte oriented. Right. It's regulated in a byte oriented way in the original version of TCP/IP. But there's another aspect of structural scalability as well. If you only have a small number of bits in the address space, or if you're exhausting the address space, you're not going to be able to increase the number of objects that you're managing. This is one of the reasons, by the way, that the IP community, the network community, is trying to get people to move from IPv4 to IPv6. You've run into structural unscalability because the address space is too small. But with a larger address space, you can expand, and you need to do that because of Internet of Things. If for no other reason, I've lost count of the number of gadgets that we have in our homes now, but each of them has its own IP address.
Yep.
So that is what I meant by structural scalability.
There's some really great nuggets that come out of this, and I just think this is a lost art. It's a lost discipline in the grander scheme of things, and I think we need to bring it back. And I think you are a great person to talk through some of these subjects. So I want to encourage people to pick up your book today and start using it on the projects that they're working on. But if somebody wants to find out more about you and the kind of information that you've provided in books or other educational classes, how can they reach out to you?
I have a website, andrebbondi.com, which has a contact me window in it.
So thanks again, Andre, for being on the program, and you're welcome back anytime.
It's a pleasure. It's a pleasure.
These kinds of shows I really love because they could keep going on and on and on. And it just means that I want to have Andre back again. But I hope that you enjoyed it as much as I did. So if you want to reach out to me about a show topic that you would like to talk about, I'm real easy to reach online. You can reach me on most social media platforms. I think LinkedIn is my most frequently that where I'm on and accessible to, and that's where I post mostly. And you can also click on, you can use that QR code and click on the link for that to see all of the ways that you can reach out to me. But you can also shoot me an email at heyscott@smcjournal.com. Would be great if you could like this channel and give me a thumbs up on this video. Maybe ring the bell so you'll be alerted when I put new videos out. Thank you so much for everybody watching the programming that we put out. I hope that you really enjoy it. And I look forward to hearing from each of you. For this episode of the SMC Journal podcast, this is Scott Moore saying thanks and bye-bye.